Okay, so what I was saying at the end of the last video when we were doing what's called proving the units is that you can't just randomly sub this in for a Tesla without showing me where it comes from. So you have to say, okay, I know from the equation F equals BIL sine theta, and this is where we define the Tesla. So this is what we can use then to sub for it. And then you can't just randomly sub for a Coulomb without showing me where it's coming from. And this is usually, actually always the one that we use when we want to go between coulombs and amps. Okay, so I equals Q over delta T, and then sub it in. Okay, so you can't just sub in things that you might like. You need to prove that they actually are equal. And only sub one at a time. If you sub too much at once, you're just going to screw yourself up. Okay, so our new equation then, now that we proved the units, is F equals QVB sine theta. All right, the force on a charged particle moving in a magnetic field. You're going to get maximum force when the V and the B are perpendicular with each other. So you're going to get maximum force when the charged particle is moving perpendicular to the magnetic field. So like in this case, the field's going in to the page and the particle's moving to the side. You're going to get, and that means theta is 90 and the sine of 90 is 1. You're going to get minimum force, which will be no force, when Q and B are going in the same direction. So if I had a magnet like this, and my charged particle is moving this way, there's not going to be any force here, okay? Because the angle between the V and the B would be 0, all right? Or it could be 180, depending on which charge the particle, which way the particle was moving. And if it was 180, it would be negative, and that would just mean that it wanted to move one way, and that you had to do work on it to move the other. But maximum, oh no, 180 is still 0. Never mind. Maximum force 90, no force when they're parallel. Okay, now the other good news, there's a hand rule. So going back to the original picture that I had drawn, here is my fields. Here is my charged particle moving this way. And for right now, let's make it a negatively charged particle. But it could be positive. Again, just going to determine your hand, which hand to use. And this one you'll be happy to know is called the right/left hand. And it's a palm rule too. Palm rule, and it's like 2.0. Okay, so it's the second version. Why? Because it's almost identical to the first palm rule. If you remember the first palm rule, it was for the current carrying wire. Point your fingers in the direction of the magnetic field. Point your thumb in the direction of the current flow, and the force will come out of the palm of your hand. So that was for when it was current. This one's going to sound awfully familiar. Point your fingers in the direction of the magnetic field. Point your thumb in the direction that the charged particle is moving in, and the force will come out of the palm of your hand. The only thing we've traded in is that instead of current flow, it's going to be charged particle. Okay, but it's still your thumb pointing there. So again, with the appropriate hand, point your fingers in the direction of the magnetic field. Point your thumb in the direction of the charged particle, and the force will come out of the palm of your hand. Okay? So what will this one be? Well, I used my left hand, so my fingers are going, I need to raise this up. My fingers are going into the page, my thumb is going down, and so my thumb is going to the, right? So the force should be going towards the bottom of the page, right? The force should end up going this way. What if I had a north here and a south here, and I had a positive charged particle moving like this? My fingers go from north to south. My thumb has to point in the direction of the flow of the particle, so this one would be going into the page. Okay? If we were doing this in real life, I'd put up like 1,000 on the board. Let's do a dot for the field. Let's do a negatively charged particle, and let's have it moving like this. So the dot means the field's coming out of the page. The negatively charged particle is moving to the top. You can't see my hand. Let me raise this up. You still can't see my hand. There we go. And my palm is going to this side, so the force would be going this way. Okay? We will practice these when I see you in person. I will probably give you a 5-minute hand rule quiz when I see you, but it won't be on these ones. It'll be on the first two that you're actually getting pretty good at. And I'll do it right at the end of class after we practiced a whole ton. So don't stress about it. It's not meant to be anything other than to see, are you grasping it? And then the next day I'll add another one in until you get really good at them. So please don't stress when I say that. And because if you do, then they'll all be surprise quizzes instead of me giving you a little warning. But it's really just seeing, can you get your hands oriented right way? For today, I have some more questions for you. They are going to be on page 508, numbers 13 to 16. And then back on 512, where you were working from yesterday, I already asked you to do 15, 16, and 17. And now we will add in maybe 20 to 23, let's say. Okay, so 508, 13 to 16, 512, 15, 16, 17, and 20 to 23. And I will put that in the sheet. Okay, have a good one.